Now, in addition to the stabilization that benzene provides to itself through aromaticity, it also provides stabilization to alkyl groups that are directly connected to it. So in this example, we have a 3-carbon chain, an alkyl chain, attached to our benzene ring. Now, this is known as the side chain. Now, the carbon that's directly connected to the benzene ring, this is known as the benzylic position. This is the benzylic carbon, and the 2 hydrogens that are also attached here are the benzylic hydrogens. Now, since this is in such close proximity to our benzene ring, the benzylic position provides stabilization to radical and carbocation intermediates. So let's take a look at a couple of reactions that this molecule can undergo involving radicals and carbocations and see how it influences the product. So first, we can take this molecule and treat it with NBS. Now, NBS involves a radical mechanism, and it's going to allow us to place the bromine that gives the most stable radical. So that's going to be a radical that forms at the benzylic position. So using NBS, we'll know that the bromine is going to be placed at that benzylic position. And it's very useful to use NBS when you're doing a radical reaction involving a benzene ring or anything with pi bonds, so you don't have to worry about Br2 reacting with the pi bonds. Now, if we were to take an alkene version of this molecule and treat it with HBr. Now, we know that HBr involves Markovnikov's rule. So let's go ahead and consider the mechanism here. The pi electrons are going to come over and take the H, giving the electrons to the bromine. Now, at this point, we want to form the more stable carbocation, which usually forms the more substituted carbon. Now, each of these carbons are technically equally substituted. They're each bound to 2 other carbons. However, this one, the benzylic carbon, would allow a resonance stabilized carbocation. So we know that the carbocation would form here, and the H would go on the other carbon. Then our bromide would come in and add to the benzylic carbon. So this would be the product of hydrohalogenation. Lastly, we could do the anti-Markovnikov addition of HBr to the same alkene by adding peroxides to our reaction. Now again, this is going to be anti-Markovnikov, so we're going to get the bromine on the least substituted carbon, or the least stable carbon, and the H will go on the most stable carbon. Now, if you go through the mechanism of this reaction as it's shown in Chapter 10, you'll see that the radical is going to form at this benzylic position, which is why we get this particular stereochemistry. Benzene side chains can also undergo oxidation. Now, we can use any type of side chain, so methyl group, we can have a group attached to an R group. This R group can be any number of carbons long. We can also have a carbon attached to 2 R groups. The most important thing about this oxidation is there has to be a benzylic H attached to our benzene ring. So if we used a structure such as this, where we would have 3 R groups attached to a carbon, this could not undergo oxidation. Now, the oxidation reagents we're going to use are the same as what we saw with the oxidation of alcohols. So chromic acid, which involves sodium dichromate, sulfuric acid, and water. Or you can use potassium permanganate with water and heat, followed by an H3O plus wash. Now, all of these molecules, so no matter what the R groups are, they're all going to result in the exact same product. So an oxidation of a benzylic side chain results in benzoic acid. And for these two molecules, it's a very important reaction because essentially we're getting rid of the R groups. So this is a carbon-carbon cleaving reaction. So it's a way to get rid of carbons from a long chain attached to a benzene ring. The last reaction we're going to talk about is the Birch reduction. And this is an important reaction because it's one of the few reactions that can destroy the aromaticity of a benzene ring without using extreme conditions. So in this Birch reduction, what we're going to do is start with the benzene. We're going to treat it with sodium metal in the presence of methanol and ammonia. And we are going to add hydrogens that are para to one another, so on opposite sides of the ring. So these two carbons that have gained the hydrogens have been reduced. They have gained electrons. So that's where the term the Birch reduction comes from. Now on the next slide, we'll go ahead and take a look at the mechanism for how this reaction proceeds. And it's actually very similar to the dissolving metal reduction reaction that we saw in OChem 1, where we converted an alkyne into a transalkene. Now, just like the dissolving metal reduction reaction, we're starting with sodium metal, which has its single valence electron, which it's very happy to give up. So it is going to donate its single valence electron to the benzene ring. So I'm going to show my arrow coming over, and it's going to be a single barbed arrow because we're showing the movement of a single electron. Now at this point, we are going to exceed the octet rule for the carbon at the top. So that's going to cause the pi electrons between the first and second carbon to break. We're going to have resonance occur. So we're going to have one electron come here. The other is going to go over here. And then that's going to cause the second set of pi electrons to also break. We'll have one come over there and one come here. So we have this cascade of electrons. Now the intermediate for this step is we will have a single electron on one side of the ring, and we'll have a pair of electrons, one of which came from the sodium, on the opposite side of the ring, and that will have a negative charge. So similar to the dissolving metal reduction reaction, we have a radical anion intermediate. Now the methanol is going to come in and act as the proton source. So we'll have the pair of electrons act first. It'll take the H from the methanol and give the electrons to the oxygen. So now we've added our first H. Then the process will start again. So we will have a second sodium ion, oops, I lost my radical, come in and donate its single electron to the single radical. And we're going to create an anion intermediate. Again with a negative charge. And then another molecule of methanol will come in and act as the proton source. And at this point, we have reduced the two carbons on the opposite side of the ring. So the most important intermediate in this mechanism is this radical anion here. So notice how we have the two H's form opposite one another, and that's because the anion and the radical have too many clashing electron density. So we want them to form as far away from each other as possible. And that's how we got the trans configuration when we reduced the alkyne into a transalkene. So a similar type of mechanism here. Now, if the benzene undergoing the Birch reduction already contains a substituent attached to it, it can influence the type of product that we form as a result. So if the group attached is an electron donating group, now electron donating groups are abbreviated EDGs, and they're also known as activating groups. And we're going to see this term a lot in the next chapter. Now, these electron donating groups actually destabilize the radical anion. So what that means is the carbon connected to the electron donating group cannot be reduced. We cannot get an H. And that's because the carbon that gets the H is the one that has an anion or a radical. This electron donating group is donating its electron density. So we already have a good amount of electron density on this particular carbon, and it doesn't need any more from an anion or a radical. So if this carbon cannot be reduced, we know that the one opposite from it cannot be reduced either. So that means the other carbons in the molecule will have to be the ones undergoing the reduction. So one of the products we can get from this reaction is one where we have H's on carbons that are not connected to the electron donating group. You could also draw it this way. But either way, these are the exact same product. Now, if the group attached to the benzene ring is an electron withdrawing group, electron withdrawing groups, also known as EWGs, and also known as deactivating groups, which we will see in the next chapter, actually stabilize the radical anion through resonance. So with these electron withdrawing groups, they're pulling electron density towards themselves. So if we have an anion form on this particular carbon or a radical, it's actually going to be stabilized by this electron withdrawing group. So that's actually going to promote this carbon being reduced. So we'll say it wants to be reduced. So this particular carbon will get the H. Now we know that this carbon will get the H as well as the one that's opposite to it, and so this one will get it as well. So the product we get when the benzene ring is substituted with an electron withdrawing group is an H right next to the electron withdrawing group and opposite from it, as well as our two pi bonds. Now, as we start to move through chapter 18, you'll become more familiar with what's an electron withdrawing group versus what's an electron donating group. But we'll go ahead and go through some practice problems involving the Birch reduction, and I'll point out some features that you can see to give you hints to what type of groups you're working with. So in our first one, we have our benzene ring, which is substituted with a carboxylic acid group. Now this carbonyl is capable of participating in resonance with the benzene ring, so it will pull the pi electrons up towards the oxygen atom. So by participating in resonance, it's actually going to make this carboxylic acid group an electron withdrawing group. And we learned on the previous slide that carbons containing electron withdrawing groups want to be reduced. Which means they're going to be the ones that have an H. Okay, so we know that this carbon wants to be reduced. We also know that the opposite carbon is also going to be reduced. So we'll go ahead and draw our product. I'm going to draw my six-membered ring first, as well as my electron withdrawing group. Then I will draw the two hydrogens that we're adding in the process of this Birch reduction. Then my two pi bonds will end up parallel to one another on the carbons that did not gain the H's. In our second practice problem, we have a benzene ring that's substituted with two alkyl groups. Now, as we're going to learn more in chapter 18, alkyl groups are slightly electron donating. And we kind of saw this previously when we looked at carbocation stability. So the more substituted carbocations were more stable because of hyperconjugation. The neighboring carbons were able to donate some of their electron density to spread out that positive charge. So it's a similar thing here. these guys are able to donate some of their electron density. So that's going to make both of these groups electron donating groups. Now we learned that electron donating groups will not allow the carbons to be reduced. So this carbon cannot be reduced, as well as the one opposite. And the other carbon containing our electron donating group also cannot be reduced. And same with the one opposite. So it really only leaves 2 carbons that can be reduced in this molecule, which is these 2 shown here. And you have to have 2 carbons that are opposite to one another. If you don't have 2 carbons that are capable of being reduced and opposite from one another, the reaction will not proceed. So we will go ahead and draw our 6-membered ring and our groups. We'll draw the H's on the carbons that are capable of being reduced, and then we'll draw our parallel pi bonds across the carbons that were not reduced. And in our last example, we have a combination. We have a carboxylic acid, which is an electron withdrawing group, and we have an alkyl group, which is electron donating. So we know that the carbon containing our electron donating group cannot be reduced, neither can the carbon that's opposite from it. The one containing the electron withdrawing group wants to be reduced, and we also have a carbon that's available opposite from it. So again, drawing our 6-membered ring, our 2 substituents. We will draw the H's on the carbons being reduced and the parallel pi bonds on the carbons not being reduced.